Hello everyone, this is John Buck back with another continuous time linear systems video. In today's video we're going to talk about the geometric interpretation of the frequency response. And what I mean by that is the way we can look at the location of the poles and zeros of the Laplace transform and understand basically in a rough sense how the frequency response should look, where we should have high values of the frequency response, where we should have low values, where we should have sharp peaks versus broad peaks in the frequency response. And again, a very similar story will come down to how close are the poles and zeros to the actual frequency axis. And so that's the story we saw before in discrete time linear systems, but what's new now, or what's changed now, is that the contour in the complex plane for the frequency response is different. In the Laplace transform story, the frequency response happens when we set s equal to j omega, that is on the imaginary axis of the response. And so let's see how we can get to this in a geometric sense if we switch over to the whiteboard. So the first step is to factor the Laplace transform of h of t, that is the system function h of s, to get the poles and zeros. So thinking of the Laplace transform as the ratio of some numerator polynomial to denominator polynomial, we say, well, if we factor this in terms of poles and zeros, we'll get some constant out in front a, and then the numerator will have, these will be the beta 1 through beta sub k will be the roots of the numerator polynomial, where we've just factored it like this. And then similarly, we'll have a denominator, where I'll call the roots of the denominator, which are the poles, will be alpha 1 through, we'll say alpha l. So again, just to label the poles and zeros. The factors in the numerator, the beta sub k's, are the zeros. And the factors in the denominator, alpha sub l, are the poles. And we can write this compactly in the product notation using capital pi. So we can say this is some capital pi as k goes from 1 to k, where capital pi means the product, just like capital sigma means a sum, capital pi means a product of s minus beta k, and the denominator have as little l goes from 1 to l, the product of s minus alpha l's. And so now if we want to look at the frequency response magnitude, right, we say that's always the most important thing. The first thing we want to know about a system in many applications is which frequencies are passed through the filter and which ones are attenuated. So I want to look at the magnitude of h of j omega. Well, I'm going to find that by setting s equal to j omega, and then take the magnitude of that. And so the magnitude of a product is just the product of the magnitudes, right? So if I scoot this up, I can make some space. So now I have the magnitude of the whole product from above, and now I'm going to break it out using that the magnitude of product is a product of the magnitudes. So now I've broken this down. Oh, I just realized these s's here should have already been j omegas. Let me fix that. And the advantage of putting it in this form is, again, a theme we've seen again in this class, is thinking about a large complicated system by a combination of first-order terms, right? We can say if I understood how one term that looks like a single first-order pole works, I could just combine them, and especially if I'm going to look at things in dB, because when I take the log, all these products and ratios will come apart into sums, right? Or I'll have the sum of the numerator terms minus the sum of the denominator terms once I take log if I go to dB. So it makes sense to think about one piece at a time here. And so we're going to start with the first order pole, because in continuous time they happen a little more naturally for first order systems. So let's get a clean page and start that. So we're going to have h of s is s minus alpha. And we're going to assume that for this case we have causal stable systems, because we're talking about frequency responses, so things need to be stable. And so again, to take the magnitude of this, we're going to replace s by j omega and take the magnitude of each side. And now we get to the point where the geometry really becomes clear, because if I think of this denominator in terms of the complex plane, this j omega minus alpha in the complex plane is the vector that goes from alpha, which is the pole, to j omega, the point on the frequency axis. So let me sketch a complex plane rather with the pole in it. So in this figure, here's my pole at alpha, right? This is s equals alpha. And then for j omega, I'm on the axis here. Right, so that green stripe is s equals j omega. And so this is the imaginary axis where we're evaluating the frequency response. So this vector, j omega minus alpha, like I just said a second ago, is the vector that runs from the pole for a given value of omega. For some specific value of omega, it's this vector here. So this denominator, the magnitude of that vector, is the length. So the magnitude of j omega minus alpha is the length of that vector. So that says, as omega, in this example, as omega increases, I'm moving further and further up this axis, right, drawing longer and longer vectors. So the denominator is getting bigger and bigger, and overall, h of omega is getting smaller. So the contribution of this pole at s equals alpha gets smaller as I move away. Now, when does that happen? Well, the sort of breakpoint we talked about earlier is when the real and imaginary parts are equal. It's sort of roughly this point I've drawn here. This is about the 3 dB point, because if say I call the imaginary part here sigma L, that this point here is the point where omega equals sigma L, so that this is a 45, 45, 90 triangle. And so this side, the length of this vector is root 2 times sigma L, which is the real part of the pole here. Well, it's the magnitude of sigma L, because sigma L is negative the way I've drawn it. But so that's that 1 over root 2 in the denominator. When I compute this, the power is a half. That's the half power point, or the 3 dB point. Right. So when omega is equal to sigma L away from the pole, in this case, this is for the example of a single real pole right on the axis. So when omega equals sigma L is the 3 dB point, or the minus 3 dB point. Right, so that's sort of the loose approximate cutoff. An actual question is, well, what if I have more than one pole, and especially what if I have complex conjugates of poles? So maybe I have second order poles. Let me draw a new page with that. So my pole zero diagram for a second order pole would look something like this. And especially if I remember the standard second order form we saw in chapter 6, we said h of s, hold on, let me fix that. Right, this is our standard second order form with the j omegas replaced by s's. We'd have s squared plus 2 zeta omega sub n, the natural frequency s, plus omega sub n squared. And then we had omega sub n squared in the numerator just as a constant for the standard form. And what I've drawn here, well, actually think about it for a minute, pause the video and think, is the case I drew here underdamped, critically damped, or overdamped? So think about that for a second. Pause the video if you need to. Right, this would be a case where I have two complex poles. Complex conjugate poles means it's underdamped. In fact, we can use the quadratic formula and go through and solve this. I'm not going to do it now. You can do it on your own to show that we can relate the locations of these poles and zeros to zeta and omega n. So for the underdamped case, zeta will be between 0 and 1. That will turn out I'll have complex roots. And when I rewrite everything, I'll have minus zeta omega n plus or minus j times omega n 1 minus zeta squared. So this real part will be minus zeta omega n. The imaginary part will be omega sub n, the natural frequency, times 1 minus the square root of zeta squared. And so here are my imaginary parts at omega sub n minus omega sub n. And so when I look at these, the other thing that comes out is if I square the real part and the imaginary part and add them, the zeta things will all cancel out, and I'll just be left with omega n. So omega sub n geometrically is actually the natural frequency is the radius of the pole from the origin. So this radius line is omega sub n large. So that one of the useful things that comes out of it is it just points everything scales by omega sub n. That zeta tells me the ratio, or sort of the split between real and imaginary parts. When zeta gets close to 0, when zeta gets very small, the poles are moving closer and closer to the imaginary axis, and the resonant frequency, this omega n 1 minus zeta squared, this will get closer to omega sub n as zeta goes to 0. So now I just told you that back in chapter 6. Now we see why it's happening. And if we think about the geometry of, say, well, how far, as I go on the imaginary axis again here, let me put my green line down. So as I'm going to higher and higher frequencies, remember we said that the magnitude of h of j omega, nope, wrong thing. Right, so the h of j omega is like the product of all the length vectors for the poles. So if I want to pick some point, let me mark a particular point on the axis here. Say right here, I'd say I'd have the length of this vector and the length of that vector, 1 over those. Let me do that as a line instead. Right, so I have the frequency response will be like 1 over each of these. And so as I get closer to this pole, as I get closer and closer to the real axis near this pole, pause for a minute and think about what do we expect is happening to the frequency response. Right, this vector isn't changing too much, right? If I sort of draw the bottom vector, we can see the length is only changing a little bit as I get up here, but this vector is getting much, much shorter. So because it's in the denominator, that pole is pushing h upwards as this vector gets short, while this one stays relatively the same length. Or certainly this one is getting shorter much faster than this one's getting longer. So it wins out, and I end up getting, if I plot my frequency response, I get a resonant peak in that neighborhood. So I'll get a peak in h of j omega in the neighborhood of omega equal 1 minus zeta squared times omega n, which again for small zeta will be essentially omega n. And so as zeta gets smaller and smaller, right, this pole is moving in towards the unit circle, and the other thing that will happen is that this peak will get sharper and sharper. And if I sort of think of why, it's because of the 3 dB points, which if I sort of say these are the regions where I get how far up and down from the pole I get to get this 3 dB down, the closer the pole gets to the axis, the tighter that triangle gets. So it says that all the action is in a narrower and narrower range of frequency as the poles move in. So in general, that's worth writing down. As zeta goes to 0, the poles move closer to the imaginary axis, and as a result, the peaks in the frequency response, like I've shown here, these peaks get tighter and sharper. And again, what's going on here is in contrast for these resonant peaks where I have this spike out at some non-zero frequency, it differs from the earlier version. Oh, which I never actually drew. That was a mistake. When the pole is on the real axis, the peak will be at 0 when omega equals 0, right? Because this point right here will be the point that has the shortest vector, so the smallest denominator, making the largest h of j omega. So let me quickly sketch. We've seen it before, the first order system, but the magnitude of h. Right, so I'll have my peak for this sort of low pass, this first order low pass, the peak at omega equals 0, and then it will decay off, but it will be, at minus 3 dB, or which would be 1 over root 2 times alpha for the magnitude of h, will happen at omega equals alpha. So when I'm making my 45-45-90 triangle here, where the imaginary part equals the magnitude of the real part, or the break point in our Bode plot is also the point where I'd be 3 dB down here on my way down. So that's the simple first order version. Again, this will get sharper if the pole got closer and closer to the origin, but it will get sharper at 0, whereas for the second order, or anything that gives me a complex conjugate pole away from the axis, I'll have this second pole, or I'll have a pole up here, and the spike will be at a frequency that's not 0. So by thinking about the length of these vectors, and particularly near a vector, it will have a stronger impact. When I'm very near a pole, it will have a strong impact pushing things up. The story for zeros is pretty much the same thing, except zeros push things down the same way we saw in discrete time linear systems. And so if I get to the neighborhood of a 0, or even could have a 0 on the axis, it will push things down. All right, so this video has gone on quite long enough, so I'm going to stop here. And we can see more examples and work on this in class on Thursday. I'll see you then.